Has started. Yes. Okay, so let's start the revision quickly. So in week 1, we have the topics of vectors and matrices, right? So vector addition and scalar multiplication, I guess they are the pretty basic things. So quickly, let's start with matrices. So for a matrix, so let us say you have a m by n matrix. What does the m represent and what does the n represent quickly? M represents the
Means
Rows
rows
of
and
Number of rows.
number of
and
rows
columns.
and
columns.
the column,
10 columns.
Number.
right? Okay. So yes. Okay. So now addition, scalar multiplication, and multiplication. These things can be done for the matrix operation. So addition, that for same size matrix we can do addition, and for scalar multiplication, for any matrix you multiply with a scalar, then it is scalar multiplication. So these two things are pretty straightforward. But what about multiplication? So suppose you have two matrices A and B, right? And suppose let us say this is an m by n matrix, and let us say this is maybe some p by q matrix. So what is the condition you need on A and B so that A into B is possible? AB is possible if and only if,
N and P
what
is
is the condition?
N and P are
N
equal.
into P.
N and P are equal.
Okay, good. All right. So this is about multiplication. Now, what about the transpose? Let us say A is an m by n matrix. What is the size of the transpose?
N by M.
n
M
by
by
n.
M.
So the rows and columns are reversed in the transpose matrix, right? Okay. And in matrix type, so rectangular matrix means that m by n matrix where m not equal to n, and square means m is equal to n. Okay, fine. And diagonal matrix means that you have some diagonal entries here. It can be 0, non-zero, or anything, but all the off diagonal entries should be 0. That is a diagonal matrix. And what are scalar matrices? Scalar matrices are nothing but all the diagonal entries are same. So these are also diagonal matrices, and we can write it as alpha times of identity matrix, right? So this is the identity matrix we are telling. And zero or null matrix can be of any order. It can be rectangular, square, or anything where all entries are 0, right? And in triangular matrix, what are the two types of triangular matrix we are having?
Upper and
Upper,
Upper and lower.
lower, right? So for upper triangular matrix, you need all the entries below the diagonal to be 0, right? So for example, if you have A11, A12, A21, A22, right? So if it is an upper triangular matrix, which entry should be 0?
A21.
A21.
A2.
A21 should be 0. So what is the relationship between I and J for this element? I is? So
I
if this
greater
is
than J.
Aij,
Greater.
I greater than
yeah,
J.
yeah. So for I greater than J, Aij is 0 for an upper
0.
triangular matrix, right? Now for a lower triangular matrix, you know that this part can be anything, but this part should be 0. So this means what? This part, so A12 here is 0. So this means for I strictly less than J, Aij is 0, right? So this is what is upper and lower triangular. Okay. Now here, what are symmetric matrices?
If matrix of A is equals
A
to
is equal
transpose
to
of
A.
A,
Transpose of A.
Yeah, so if A transpose is equal to A. So this means what? Aji is same as Aij, right? So these are symmetric matrices. And what are skew symmetric matrices?
A
A
transpose
is
to minus.
minus A transpose.
Yeah. So A transpose is equal to minus A, right? So here what happens to the diagonal entries first of all? What about the
AI.
diagonal entries? What do you know about diagonal? Yeah. So
AI
you know,
is equal to minus Ij.
so for a skew symmetric matrix, the diagonal entries are 0. Okay, so these are some special type of matrices, right? All right. Okay, so now let us start with some simple problems. So here we have two matrices B and C. Okay, which of the following options are true for A such that AB is equal to C? Okay, so first of all, what should be the size of the matrix A? What is the size of the matrix B first of all?
3 cross 2.
3 cross 2.
This is a 3 cross 2 matrix. What is the size of the matrix C?
2
2 cross 2.
2 cross 2.
Okay, so what you are having here, so A times of B, so B is 3 cross 2, is a 2 by 2 matrix. So what should be the size of
2
A?
cross 3.
2
2
cross 3.
cross 3.
A should be something like a 2 by 3 matrix. Okay, now whether such a matrix exists or not, if it exists, whether it is unique or not, so this is the question. So first here A should be a 2 cross 3 matrix. Okay, and whether such a matrix exists or not, we have to check. So let us take A to be, so it is a 2 cross 3 matrix. So you have how many rows? 2 rows. So A11, A12, A13, and then A21, A22, A23. Okay, now if I'm going to do AB equal to C, then what will I get? A times of B. What is your B? This is your matrix B. So if I multiply this with the first column, what will you get? A11 minus A13. And if I multiply it with the second column, what will I get?
A12.
So I get A12. Okay. Now the second row with the first column will give me A21 minus A23.
3.
And the second row with the second column gives me A22. Right? So from here, we can now equate it with the matrix C, which is 0, 0, minus 1, 2. Now we can equate the LHS and RHS. So you have A11 minus A13 equals 0, A12 equals 0, A21 minus A23 is equal to 0, and A22 equal to 2. So now these two are fixed. Now what about these entries, remaining entries? What we know is that A11 equal to A13,
Ma'am,
here it is minus,
A2 minus
yeah,
1.
yeah. So this is minus 1. So A21 is equal to minus 1 plus A23. Right? Only this much information we have. So here, for example, so here you see that A11 and A13 can be both 1. Right? And what about this? Suppose A23 is 0. What about A21?
Minus 1. Minus 1.
Yeah. So if A23 is equal to 0, then A21 is minus 1. So these are all the possible, one possible choice. How many such possible options are there?
3.
Infinite.
Infinite, right? Because you can, because you see, instead of 1, I can put 2, 3, 4, 5 or any real number, right? Same way you can have any choice for A23. So how many solutions actually we are having for this? Right? Infinitely many, right? Because this can be any real number. You can choose it to be K, where K is any real number. Similarly, here this you can choose it to be some L, where this is any real number. So this way, we will get infinitely many such matrices. Is that clear for everyone? Yeah?
Yes, ma'am.
Ma'am, can you explain from this step A11 minus A13? Like how did this came?
We are just equating it component wise. So you see that this component, we are matching it with this I am matching it with this I am matching it with this, and this I am matching it with this.
But ma'am, how did you get A11 minus A13? Why A11 minus A13?
A into B. I just did the matrix multiplication. A into B. So the first row and first column, that is how we do the matrix multiplication, right? Just simple matrix multiplication. How do you do A into B?
That is in the question. AB is equal to C.
AB equal to C is there given to you, right?
Okay.
So I am doing A into B. So A into B, the matrix multiplication. How do you do the matrix multiplication? First row, first column gives this first entry, right?
Ma'am,
A1.
here you take
Okay,
column.
okay, ma'am. I get it.
Okay.
Here you take 2 cross 3 matrix, no? A,
Yes, A is a 2 cross 3 matrix because of
because we
given
multiply with
condition.
this, so we get 2 cross 2, right? That's why.
Yes, yes. From the given condition, we have already obtained a 2 by 3 matrix. A should be a 2 by 3, and hence I have taken this structure. Okay, fine. Okay, so such a matrix does not exist is incorrect, and there exists a unique matrix that is also incorrect. Okay, fine. All right. So now in general, if you have a system of linear equation, okay, so you know that we have a matrix representation like this. So where this we call it as the coefficient matrix. So here in this, how many equations do you see?
M equation.
So we see m equations, and how many variables are there? We have
N variables.
And variable.
okay. So here we have a coefficient matrix and an unknown vector, right? So this is the way we write the system of equation in the matrix representation. So the same can be expressed as Ax equal to B, right? Okay. Now suppose we are considering a specific scenario where we have two equations and two variables. Okay. So in this scenario, what are the possible cases? So only these are the possible cases. So what is the first scenario? First scenario is the case where we have two equations. So this is the equation. So this is equation 1. This is equation 2. So both are parallel, right? So if equation 1 is represented. So if they are parallel, what do you know about the solution?
No
No solution.
solution.
No solution. Okay. Now here this is equation 1 and this is equation 2.
Unique
Unique
solution.
solution.
Unique solution. So and in this case, the intersecting point gives you the unique solution. Okay. And what about this case? So
Infinite solution.
the
Infinitely
same m represents both equations, right? Represents both equations, right? So in this case, all points on the line, all points, so which is infinitely many, right, are solution. So you have infinitely many solution in this case, right? So here you see that if it is unique or infinitely many, we call the system to be consistent. And if there is no solution, we call it inconsistent. Right? The system is consistent if either it has a unique solution or infinitely many solutions. In these two cases, the system is consistent, and here it is inconsistent. Okay. So now if you look at the matrix representation, okay, what can you say about the determinant of the matrix in this case? When you have no solution, what can you say about the determinant?
Determinant 0.
Determinant is 0. What can you say in the case of a unique solution?
Determinant not equal. Not 0.
And again, when you have infinitely many
0.
solutions, again you have a 0 determinant. Okay. So these are some observations you have. Okay. And again, what about the rank of the matrix? Rank is there in week 4, but just since it is related here, I'm just using it. So what should be the rank in this case? So let us assume that A is non-zero. Okay. What should be the rank here?
2.
Are you sure?
If determinant is not 0, ma'am.
Here, determinant I have written equal to 0 only.
Rank is less than 2, ma'am.
Yeah. So it has to be actually 1 because A is non-zero, or you can simply write less than 2. That is also fine. Rank of A is strictly less than 2. And here what should be the rank?
Ma'am, why less than 2, ma'am? Size of
2.
A is
See, that is the usual case, right? So suppose, so these are some equivalent conditions. So take a system of linear equation Ax equal to B. Okay. So you have unique solution if and only if, so let's assume A is an n by n matrix. So determinant of A is non-zero if and only if rank of A is equal to n. Now, if you have infinitely many solution or no solution, in this case, the determinant is 0, and in this case, you have rank of A strictly less than n. Okay, so this is the usual condition we have for any system of linear equation. Okay, now
So,
here,
ma'am,
yeah,
One second.
sorry, can I just ask you something, ma'am? See, in this case, like where you represent a system of equations as Ax is equal to B, and let's say B is not equal to 0, which means it's not homogeneous.
okay,
So even in that case, we only take the determinant of the coefficients, right?
exactly.
So no matter what B is,
Yes, yes,
even if B is not equal to 0, we still continue to take the determinant of just the
A,
coefficients.
yes, yes.
Okay, thank you, ma'am.
Okay. All right. So here, these you can see that here it should be 2 in this case. Yeah. What's the question?
Ma'am, just go little up, scroll little up. I was just taking a note. 1 second, ma'am. The red one that you wrote.
The last thing you wrote, ma'am. Can you just explain this once again, ma'am, if you don't mind?
I guess I have a separate slide where I have considered all these cases separately. Let me just quickly see whether it is there in week 1 and 2 or in a later week. If it is a later week, I would have covered it maybe in a later session. Otherwise, oh, it's here. I have covered it in detail here. So maybe we will have a look at it here. Okay. So if you want here, I can just quickly repeat what I told because it's something important. Whenever you have a square matrix Ax is equal to B, you either have a unique solution or you have infinitely many solutions. Okay. And here when you have a unique solution, okay, unique solution means either the determinant, in that case, the determinant must be non-zero and the rank of A must be n. Or if you have an infinitely many solution or no solution, either one of this, or in that case, determinant must be 0 and the rank is strictly less than n. So these are equivalent conditions and these are also equivalent conditions. Okay, so these are the only possible cases for a system of linear equation. Okay, and in this case, your n is equal to 2 and hence when determinant is non-zero, the rank is equal to n and which is 2. And here you see determinant of A is 0, you have infinitely many solutions. So rank of A is strictly less than 2. Is that clear now?
So whether you have no solutions or infinitely many, it's less than n.
Yes. Okay. So what is the difference between these two cases? These two conditions look the same. But why here we have no solution and why here we have different solution? That is because that depends on B. So now after this condition, the B determines whether we have no solution or infinitely many solution. Okay. So if B belongs to the range of A or the column space of A, B belongs to column space of A, or maybe I don't know whether column space comes in week 4 or week 5. So better I will use span of columns of A. Span is anyway covered, so I will use this span of columns of A. Then you have infinitely many solutions. Okay, but if B does not belong to span of columns of A, then you have no solution. Okay, so for example, very simple example I will show. So let us take this matrix 1 1 1 1. What is the determinant of this matrix?
0.
Determinant is 0. Okay, rank is 1. Okay, now for this let us take x1 x2. Okay, and here I am taking 2 2. Now you can clearly see that 2 comma 2 is 2 times of 1 1. So this means it belongs to the span of columns of A. Now does this have a solution? So you have x1 plus x2 equal to 2. Do we have a solution for this? Yes, infinitely many, right? Yes or no?
Yes, ma'am.
Yes,
We can
ma'am.
have
Ma'am, rank
infinitely
is
many.
a column, right? So how is it one if rank
Right, ma'am. Because here rank is 1 because you have only one linearly independent column or row, right? Okay.
Okay, okay.
So, ma'am, in the case of a rectangular matrix where you have like m into n, there in this particular situation, if there is no solution, then the rank has to be less than the smaller of m and n, right?
Yes, yes. It cannot be having full rank. Yes.
Okay.
And the
So,
other
ma'am,
thing
can
is
you
that,
explain
yeah, let me complete this part
when?
first of all. Yeah. So here the other part is that in this place, you see that this is your B and B is a multiple of one of the columns of A. So this condition is satisfied. But here, let us consider another scenario for the same A where this B is something different. Let us say 1 0. Okay. Now this B does not belong to span of 1 comma 1. Right? This B does not belong to span of 1 comma 1. So we don't have any solution. Why? You see that when we write this equation from here, you see that x1 plus x2 is 1 and x1 plus x2 is 0. So this implies that 1 is equal to 0. Is this possible?
No,
This
ma'am.
is not. So this is not possible. This means no solution.
Yes,
Okay.
ma'am.
Got it?
Ma'am,
So
ma'am,
yeah.
So, ma'am, can you explain in the
how
first rank how A is equal to 1? But you said it before, like rank A should be less than equal to n.
Not equal to. I never said equal to.
No,
Ma'am, if
less
there is a
than.
x1
It's strictly less
equal,
than means it cannot be equal to 2, right? But anyway, here you straight away look at the matrix. If you look at the matrix and take the columns, how many linearly independent columns are there?
ma'am, how
One.
can we visualize this no solution, infinite solution, unique solution in terms of ranks?
See, that's what I said. Only with rank, only with this condition, you cannot say whether you have infinitely many or no solution. Only thing you can say is that it cannot have a unique solution. When the rank is strictly less than 2 or determinant is 0, you can say that it cannot have no solution. But whether it has no solution or infinitely many solution depends on B. If B belongs to column space, then you know that it has infinitely many solution. So here you see that this means that it has infinitely many solution. And if the B does not belong to the column space, then you see that it has no solution. Is that clear?
if it is written
So,
x1 plus
ma'am,
x2 is equal to 1 and in second also equal to 1, then it is an infinite many solution.
Yeah, you see that you have a, this is the equation of a line, right?
Yes, ma'am.
Yeah, so I told you this is in the case you have the same line representing both the equations.
If output is coming same, then we can say that it is an infinite many solution, right?
It's I don't know how whether your statement really makes sense. The thing here you need to know is that this just represents all the point on a straight line. So all points on a line means you have infinitely many points and hence infinitely many solutions. Okay. So here
Ma'am, this,
there is no contradiction. Here you have different values and hence you have no solution. Okay.
What would be the case when there is a unique solution? I mean, how would the B look?
See, in the unique solution case, the thing is that you have rank is equal to 2. So all B is in column space. Belongs to all B belongs to span of columns of A. Because rank is 2. So it does not matter which B you are considering. Because your rank is 2, all B will be there in the column space. Because you see, what is the span of the column? Span of the columns of A is simply R2, entire R2. Rank is 2 means what? The column space is entire R2. So any B is there and already in the column space. So there is nothing to worry about what is your B in this case.
And can you represent in equation form?
You like an example like this.
Yes, ma'am.
See, I don't think this session is going like a revision session. This is going like a first instructor session for week 1, which is not at all good. Okay, fine. Anyway, so I don't think I will be able to cover everything. Anyway, I'll try to cover as much as possible. Let's take this case. So, what is the determinant of this matrix?
-1.
Minus 1. 1 minus 2, so minus 1. So you know that you have a unique solution for any x is equal to b. How can we see? So you have x1, x2 equal to b1, b2. So we can have any b1, b2. Okay. Why I am saying this does not matter is that, what do you know if determinant is non-zero? If determinant is non-zero, a
Rank is
inverse
equal to.
exists. That is the other thing. If determinant
Excuse
is
me, ma'am. Could you
non-zero,
please just show where you have written about the rank? I have a query.
just give me a minute. So if determinant of A is non-zero, A inverse exists. If A inverse exists, so what happens? Ax is equal to B will give you x is equal to A inverse B. So whatever is your B, you simply have to compute A inverse and multiply A inverse B to find the solution. And this is your unique solution. Because the inverse is unique, so A inverse B is also unique. Okay, so this is the unique solution, and hence you see that whatever b1 b2 you will have in this case, it does not matter, you will still have a solution here because you have an inverse in this case. Determinant non-zero guarantees the inverse existence of inverse, but here we don't have the inverse, so we cannot do this. Okay, so what was the question from the other student?
If
Ma'am, suppose here
determinant
is the A matrix
is
given as
non-zero,
1, 1, 1, 1, and here we are writing the rank, but before finding the rank, we must find the row echelon form, and then only by the number of non-zero rows we can get the rank. So from
See,
the original matrix itself,
row echelon form is one way to compute rank. Okay, row echelon way is one way to compute the rank, but that is not the only way to compute rank. So rank has many different ways you can compute rank. So rank of A, this will be discussed in week 4 actually. Okay, so don't worry, rank of A can be computed using row echelon form. It is the dimension of the column space, it is dimension of the row space, or you can say that number of linearly independent rows or columns. This is another definition which I have used in this case.
from the linearly independent part only, I'm asking the linearly independent part we find from the row echelon form only, like the
No.
the
You
columns
don't need
which.
row. See, you need row echelon form for very big matrices. Here you have a very simple matrix where you straight away are able to see these are the two columns, and these two columns, they are obviously linearly independent because they are in fact the same. So here there is no need of row echelon form. Row echelon form is required where you have a big matrix and you are not able to visualize the linear independence straight away. Okay.
Means here only how did we see that these two are independent, because one column can be expressed as a multiple of other, like one.
Exactly. That's the reason.
Means
So
here they
ma'am,
are
in
not
this
independent.
They are not independent. Yes.
ma'am, in this matrix, the rank A should be equal to 2, right?
2 means you should have two linearly independent columns, but here you have only one linearly independent column.
Okay.
Ma'am, rank can never be zero, na ma'am?
Rank is 0 for a zero matrix.
Zero matrix only. Okay.
Yeah, only for the zero matrix, rank is 0.
Excuse me, ma'am.
Yes.
Just a humble request. I was in the middle discounted. So could you just mention the rule about the rank and the thing you told? I don't need the explanation because I have understood. But just the rule could you please tell so that I can write down? In some I'm making mistakes actually based on
This
this.
one?
Yes, and that is the general concept. Basic you told that if a unique solution exists, then determinant of A not equal to 0. This one
Yes.
I got. But
Yes.
below that you are explaining some things. That point I got disconnected. This just the rules. I don't need
Sorry,
the.
already we are moving very slowly. So let's move ahead. I recommend you to go back and watch in the live session because others are also waiting here. Okay, fine. Okay, let's move to this problem. Match the system of linear equations in column A with their number of solutions in column B and their geometric representation in column C. Okay, so here you have the first equation. So first equation, so how can we represent what is a matrix here? You have 1, 1, 1,
One,
minus
1
1,
minus 1,
x by.
x, y, 3
2
minus 3,
minus 3.
What is the determinant of this matrix?
minus 2.
0.
Yeah,
Minus 2.
it is non-zero. So do we have a unique solution?
Yes, ma'am.
Yes, ma'am. Yes.
So we have a unique solution, right? So this means, so here, this is the answer, and here you see, this is the case, you see two equations with a unique solution you have. Okay, and for this case, second case, you see the LHS are same for both the equations. So in that case, this imply that
No
1
solution.
inside 7. So
No
this is
solution.
not possible. So no solution. So no solution. Okay, so it means that they are parallel planes. By the way, what is the general form for a plane?
ax plus by plus c equal to 0.
Ax plus by
Ax plus by plus cz equal to d. Okay, and if d equal to 0, plane passes through origin. Okay, so here you see that in this case you have, so this represents two parallel planes. Okay, so here we have no solutions because they are parallel planes. They do not intersect. Okay, and for this one, here you have z equal to 0 and x plus y is equal to 1. X plus y plus z equal to 1. So this means you have the set of all x comma y comma z such that both these equations are there. So this means it reduces to just x plus y is equal to 1 and z is equal to 0. Right? So this means what? You can actually make x comma y, x comma y comma 0, where you have y is equal to 1 minus x, right? So this means, again rewriting, it is x comma 1 minus x comma 0. Where x is in R. So you see that now this represents a plane. So sorry, this represents here you have infinitely many points for this solution. So you have infinitely many points, so they are the intersection of these two things. So this is the z is equal to 0. So you have the xy axis, xy plane, and the other plane is this. Okay, yeah, so there are some questions. Yeah, students who have raised your hands, please ask your question.
Option 3, just could you please explain once? 1 and 2 I understood.
Okay, so here option 3, what are we having? We are having z equal to 0 and x plus y plus z is equal to 1. These are the two equations, right? So now, so the set, what are the solutions for both this equation combined? Set of all x comma y comma z satisfying both the conditions, right? Satisfying both the condition. So now I am going to substitute this 0 in these places. So I have x comma y comma 0 and I have the other equation here. Okay, now I'm going to further rewrite this. So here I can rewrite it as 1 minus x because y is equal to 1 minus x comma 0. So now this is the solution for this system. Okay, so all possible, so whenever whatever x you put, the resulting vectors are solutions for this system of linear equation. Okay, and hence you see that you have infinitely many solutions in this case. Okay, so here you have infinitely many solutions. Okay, fine.
But infinitely solution, I understood that any x we put we will get, but from the figure it seems that only a particular portion, a particular line has intersected.
Yeah, see, that is the one. See, the intersection is a line, right? That is what you are saying, right? Yes, it is a
Yes.
line because here you see that it is x times of 1 comma 1 minus 1 comma 1 comma 0. I can put maybe writing it
Okay, so the
incorrectly.
line contains infinite points in R. Is it like
Yeah,
that?
so 0 comma 1. Just a minute, I will complete this. So 1 comma minus 1 comma 0. So this is how representing a line. This represents a line which is shifted from this line. So this is a line passing through origin, and when you add 1 point to this is a shifted line. So this represents a line in R3, right? So the intersection is a line, but even if you are considering it as a line, so how many points can a line have? It has infinitely many points, right?
Okay.
Okay, fine.
Okay, ma'am. Option 3 understood. Just could you please go back to the previous page? Just one small query here. The previous page. Yes, ma'am. Could you please just briefly tell that without computing means the row echelon, how did we see the rank here? Like number of what that time I couldn't hear. Just could you please mention that part?
See, rank is the number of linearly independent rows or columns. So
Okay.
here you have two columns, C1 and C2. So C2.
But they are not independent.
Yes. So only one, if you take 1 comma 1, any non-zero column is actually considered as a linearly independent column. So only one linearly independent column is here. So rank is 1.
Okay.
Then?
Yes.
Okay. All right, so determinant, already you people know the formulas for determinant, so let me not spend the time for explaining the formulas and all.
Excuse me.
Yes.
I just have a question with the last question.
Yes,
like
yes.
the last question. So like when there are among three coordinates, when we have 1, 0, we can like conclude that it is definitely intersecting with the line, right? Irrespective of whether x is 0 or y is 0 or z is 0.
Yeah, so instead of z equal to 0, if you have either x equal to 0 or y equal to 0, yes, you will still have the intersection to be a line. Yes.
Yeah, like when we have a simplified vector, like in the third line, x, 1 minus x and 0. If only one of those is 0, it's definitely a line, right?
Yes.
Thank you.
Okay. Okay, so what is the determinant of identity matrix quickly?
It's 1.
1.
Yes.
1.
What is the determinant of A transpose in terms of determinant of A?
Equal to
Determinant of A.
Same.
Same as A.
Same. Okay. Suppose you have two matrices. What is determinant of A into B?
Determinant A into determinant B.
Determinant of B.
Okay. Now suppose you have n matrices A1, A2, An. Now what is the determinant of this product?
Determinant of A into
Determinant of A
determinant of
power n.
A2 to determinant of A3, so on.
Yeah. So you can extend it to any finite product, right? Okay, good. Okay. What is the determinant of inverse of a matrix in terms of the determinant of the matrix?
Determinant of A.
Determinant by determinant.
Determinant of A.
Okay, good. Okay. Now, what is the determinant of A power n in terms of determinant of A?
Determinant of A into raised to power n.
Whole power n. Good. Now, what about determinant of A transpose A in terms of determinant of A?
Determinant of A square.
Because here you can first of all split it in this way, and then further you know that this is same as determinant of A, and hence this is determinant of A the whole square. And what about the determinant of this matrix?
Determinant of A.
Determinant of A. So these are some properties of determinant which we are using very often, right? Okay. So what is the determinant of triangular matrices?
Product of the
Multiplication
diagonal
elements.
Exactly. Product of diagonal entries. Okay. What is the determinant of a matrix with a zero row or column?
Zero.
Right? Okay. Good. Moving to what are row operations. So we say that if we switch two rows or if we multiply one row by a non-zero number, remember we are multiplying by a non-zero number. Multiplying by zero number is not allowed in row operation. and then replacing a row by a multiple of another row added to itself. Something like, for example, Ri replaced with Ri plus alpha times of Rj. So this kind of an operation is what is mentioned here. So this is like Ri replaced with alpha times of Ri where alpha non-zero. So this is Ri switched with Rj. Okay, so these are the row operations we have. Okay, fine. Now, what are the corresponding changes in the determinant when we are doing such row operations? So switching two rows means, so suppose let us say you have performed this row operation, first row operation. Then what happens? Then the sign of the determinant change. Okay, so the determinant sign changes. Okay, and so a second property, multiply a row by a number, non-zero number, then the scalar multiplication of a row by a constant t multiplies the determinant by t. Okay, and the last one, it does not affect the determinant. Okay, so this operation can be done without affecting the determinant. Okay, so these are the properties of determinant when we do row operations. Okay, now with this properties, what we can see, do here, let's see. If A is an n by n matrix and B is equal to alpha times of A for some constant alpha, so remember here alpha is non-zero, then determinant of B is alpha power n times of determinant of A. Okay, so based on the above property, we have this condition here. Okay, now how can you use this condition for doing this problem? So determinant of
27.
3A should be 3 power
3. 3 power 3.
into determinant of A. So this means K should be 27. Okay, fine. All right. So let A be a 3 by 3 matrix with non-zero determinant. Okay. If B is the matrix obtained from A by multiplying first row by T, then determinant of B is
T times
T
times
so here also
T times
zero.
determinant of A.
Yeah, so T times determinant of A. So anyway, if T is 0, then this is going to become 0. So anyway, fine. Okay. What about this? If C is a matrix obtained from B by interchanging first row with the
Negative
determinant
sign.
yeah,
minus
so
determinant of B.
minus
Minus
determinant of D, right? And which is minus T times of determinant of A.
But it's the first with the third, right? So that's two rows, no? If it's two rows, then does the sign change?
Sorry, what?
It's first row, you're changing it with the third, not with the second.
It does not matter with which row you are interchanging. Just two rows are interchanged. That's all. Okay, it does not matter.
If switching takes two times.
No, but if the switching is happening twice,
No,
then
it's not happening twice. See, for example, you are having a 3 by 3 matrix. So 1, 0, 1, 2, 1, 3, 1, 1, 1. Let's say this is your matrix A. What this operation does is, okay, so it simply switches the last row to the first and first row to the last. This row is going to remain in its place. So only one row operation, one row switching has happened here. Got it? So here R1 interchanged with R3. Got it?
so the sign doesn't change in this case.
Sign changes. That's why determinant of C is minus determinant of B.
Okay. I mean, the other way around. I really thought like if there's like two rows you're jumping, then sign does not changes what I was I thought.
Okay. All right.
Thank you, ma'am.
Fine. Okay. Good. Okay. If a matrix A contains a row which is a multiple of another row, then determinant is 0. Right? This you know, right? Because you have like two linearly dependent rows, so determinant is 0. Similarly, if a matrix A contains a row which is a linear combination of other rows, then also the determinant is equal to 0. Right? So these are some observations from which can help us to reduce time in computing determinant. Okay, fine. Okay, so This was not the intended PDF because I tried to reduce the number of problems because there were too many in this PDF.
Ma'am,
Yes, just give me a moment. Hold on.
whenever we change row, we change sign.
Whenever we change row, yeah, the sign of the determinant changes. Yes.
Whether it's first, second, or third, how many times we want to change, then we change it.
Yes. Yes.
With changing sign
Yes.
and column also.
If we are interchanging columns, then also the determinant changes its sign. Yes.
Ma'am, can we attempt this one? I find that it is difficult.
Sorry, what?
Ma'am, can we attempt
If you are changing 2 times, then it's not affecting the determinant, right?
What is not affecting the determinant?
If you're changing the row 2 times.
Yeah, suppose you are doing this interchanging rows another time, then the determinant will not be affected. Yes. Okay, fine. So actually these problems were like so many were there. So I wanted to skip through few problems.
In the first question that appeared, yes, this one, madam. I saw there's an activity question as well, but was finding very difficult to solve. At least
Okay, then we'll do this. Yeah, we'll do this. See here, what has happened here? So the matrix, original matrix is this. This is your matrix B. This is your matrix C, D, and E. Okay. So here for B, what is the row operation which? What is the row operation which we have done here? So can you identify the row operation done in B?
R1 minus R2.
R1 minus R2.
So in B, R1 replaced with R1 minus R2. So this kind of a row operation, will it affect the determinant?
No.
No. So determinant of B is same as determinant of A. Okay. What is the row operation done in C?
C1 minus C2.
Similar kind of a column operation. So this will also not affect the determinant. Right? Okay. So are there any specific row operation which you can identify in D and E?
No.
In D and E, there are no specific row operations.
okay. Okay, got it, ma'am. Thank you.
So we cannot say determinant of D and E may be different from E. May be different from determinant of A.
Okay. Okay, ma'am. Thank you. Ma'am, there was another question with a very large numbers, 2025, 2000.
I have considered that question here. We'll do that. Okay. So this question, if the sum of all the elements of each row of a matrix is 0, then A is not invertible. So in other way, we are saying that determinant of A should be 0. How can we see this? If the sum of all the elements of a row of a matrix is 0, then the determinant is 0. Why? How can we see this?
Linear combination of all the elements of one row is
Yeah, so one column will be a linear combination of all other columns, right? So if you have row sum, for example, for a 2 by 2 matrix, if I show, so A11, A22, A12, A21, A22. Now given that sum of each row is 0. So A11 equal A11 plus A12 is 0. A21 plus A22 equal to 0. So this means what? A12, A22 is minus A11, A21. Yes or no? So one column is a multiple of the other column. In case of larger matrix like 3 by 3, 4 by 4, the last column you can write it as a linear combination of the other columns, and hence the determinant is 0. Fine. So this is correct. Okay. Fine. If E is a matrix of order 3 by 3 obtained from the identity matrix by a finite number of elementary row operation, then E is invertible. What do you say?
Yes, ma'am.
The determinant. signs and values can change, but if it is non-zero, it will remain non-zero, right? Oh, so this is also fine. All right. What about the third option?
False.
No, ma'am.
False, right? Any system
No, ma'am.
cannot have one solution. There are systems with no solution, so definitely incorrect. Okay. What about the fourth and fifth option? So what is the formula you know for the inverse of a matrix? Finding the inverse in terms of the adjoint.
1 by determinant of A, adjoint of A.
So A inverse is equal to 1 by determinant of A
Into the adjoint.
Joint of
Okay. So this means that determinant of A inverse is equal to determinant of, so let's call now, let's say that this is some alpha. This is some number, right? I call this number as alpha. Okay. So this number is some alpha. So what I'm going to do is that I'm going to write it as determinant of alpha times of adjoint of A. So if I have alpha, you know that then it becomes alpha power n. So this is 3 by 3. So yeah, alpha cube. Determinant of adjoint of A. Right? Now alpha cube is nothing but 1 by determinant of A cube. Now I am going to bring this alpha cube to the other side. Then what happens? So from here you see that determinant of adjoint of A is nothing but determinant of A inverse into 1 by alpha cube. But what is alpha cube? 1 by
determinant of A.
Yeah. So this is nothing but determinant of A inverse into determinant of A cube. Correct?
Yes, ma'am.
So this, when we use the properties of matrix multiplication and determinant, what will we get?
Determinant A square.
Determinant of A square. So what is determinant of A given to be? 3. So it should be 3 square. So answer is this fine.
Ma'am, is there any formula for this?
Is
So
there
ma'am, for
any?
determinant of A inverse, you took it as determinant A raised to -1.
Yes.
Okay.
Okay. So here this is 1 by determinant of A, and hence you get determinant of A square. Okay. All right. So here just understand. Yeah.
Ma'am, the above can we use like a formula? Like if it's a 3 cross 3 matrix, then the determinant of adjoint of A is square.
Yeah. Yeah.
Okay.
Okay.
Thank you, ma'am.
Yeah. So this is
Can
basically
you tell again how option 2 is right?
option 2. See, what happens when we do this row operations, the determinant either changes the sign or gets multiplied by a non-zero number. So changing the sign or multiplying by a non-zero number will not make the determinant 0. So if the determinant earlier the first matrix originally we are considering is identity matrix, and the identity matrix we know that the determinant is non-zero. So after row operations also, so after finite row operations, determinant of I will be some alpha, which is non-zero, right? Because either we will change sign or we will just multiply with a non-zero number. So this will remain non-zero, and hence it is invertible. Okay?
Okay.
Okay. So let's try to answer this question. These are the row operations given here, and these are the kind of equations given to you. Now, if matrix B, okay, is obtained from matrix A by an elementary row operation of type 1, interchanging rows, then equation 1 is satisfied. Is that correct? Determinant of A equal to minus determinant of B?
Yes, ma'am.
Yes, ma'am.
Okay. If matrix B is obtained from A by an elementary row operation of type 1, so this is type 1, followed by an elementary row operation of type 2, then equation 2 is satisfied for some C.
Yes, ma'am. Yes, ma'am.
Okay. If matrix B is obtained from A by an elementary row operation of type 2, then equation 3 is satisfied. Type
No.
matrix. No, right? Because what happens? Determinant of B in this case should be what?
C times determinant.
A times determinant of.
Yeah. Okay. If matrix B is obtained from A by an elementary row operation of type 3, then equation 3 is satisfied. So type 3, equation 3. Correct or not?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Good. All right.
So once again show type 3 and equation 3.
So this is the third type of row operation which does not affect the determinant, and hence this is correct.
Yes, ma'am. Yes, ma'am.
Good. Another simple problem based on determinant. Let A be a 3 by 3 real matrix whose sum of entries of each column is 5 and sum of first two elements of each column is 3. Which of the following statements are true? Sum of each entry of the column is
All are
5.
true, ma'am.
1, 2, 3.
No, all are true.
One, two, three.
Ma'am, 1, 2, 3.
1, 2, 3, 4.
What should be the determinant in this case?
M0.
Yes. Right. So because you see this condition makes the columns linearly dependent, and hence the determinant is 0 in this case. So if it is 0, it is a multiple of all these numbers.
All the options.
Okay. So just like we saw in this case, right? This some condition like this makes the determinant 0, and hence all the options are correct. Okay. Fine. So this is the determinant formula in terms of the minor and cofactor. So let's not go into the definition. So I've just given the definitions here. Now, based on the problem we have seen earlier, let A be a square matrix of order 3 and B is a matrix that is obtained by adding L times the first row of A to the third row of A and adding M times the second row of A to the first row of A. If determinant of A equal to N, find out the values of this. So first of all, what is the determinant of B?
It should be same.
Yes, because what is happening here, first we are doing adding L times the first row of A to the third row of A and adding M times the second row of A to the first row of A. So it means R3 we are replacing with R3 plus L R1. Similarly, R2 we are replacing with R2 plus M. So here so R1 replaced with R1 times of MR2, right? So this type of operations does not affect the determinant. So the determinant will remain the same. Okay. So determinant of B is same as determinant of A. So what should be the answer here? K power 3 determinant of
A.
square into determinant of A inverse, which is K cube.
K cube determinant of A.
So K cube N is the answer.
Ma'am, can you discuss the previous questions once more?
Which one you want me to show?
Previous questions, please. Yes, ma'am. This question. How data is equal to 0?
Okay, so we are having a 3 by 3 matrix whose sum of entries of each column is 5. So what does this mean? Sum of each column is 5. So you have a 3 by 3 matrix. E is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Now sum of each column. So column wise, if you add them, so sum of each column, right? So in this way, if you add, you know that the sum is 5, 5, and 5. So when you add them, you will get 5. Right? So sum of each entry, sum of entries of each column is 5. So now if this is 5 and also you are given the first two elements of each column is 3. So this sum All this sum, they are 3. Right? So if this is 3, then what can we do?
Last element will be 2.
Yes. So what should be R3 first of all?
A31, A32 and 2.
Not R3. The column, what can you say about the last column? What
2, 2,
should
2.
be the
It will be, ma'am, 2, 2, 2.
Yeah, so column 3 is actually simply 2, 2, 2. So this we know. So this is column 3 is 2, 2, 2. Okay. Now, what can we do with the first column? So let's say R1 replaced with R1 plus R2. What do you know about R1 plus C1 replaced with C1 plus C2? What does this operation do? What do you know about C1 plus C2?
Is equal to 5.
Yeah. So this means the
3,
first
3, sorry,
column,
3. Is
the
equal
first
to 3.
column is becoming 3, right? And second column, it can be something, it does not matter, but the third column is
Understood.
2, 2, 2. Yeah. So you see that,
Understood, ma'am.
yeah,
Yes, ma'am.
linearly
Thank you.
independent, and hence determinant is 0. Okay.
Yes, ma'am. Okay, thank you, ma'am.
Yeah. All right. So this was the question someone was asking, I guess. Yeah.
Yes, ma'am.
Okay, so now consider the following matrices. This is again a very simple question only. The numbers are only scary, but when you observe the properties, the answer is very straightforward. What is the relation you observe between the matrix A and matrix B?
R1 and R2 are exchanged.
Changed with R2.
So
R1, R2 interchange.
if this happens, what is the relation between determinant of B and determinant of A?
Determinant of A
Minus
minus
A.
Negative of B.
Negative.
Minus determinant.
Minus of
Negative.
determinant of A.
So the option 1 is incorrect and option 2 is correct. All right. Okay. Now, what is the relation you observe from option matrix B and matrix C?
4 times.
2 times.
Row
Two
1 is
times row
2
1.
times. 2 times.
Yeah. So row 1 is replaced with 2 times of row 1. So this means what is the relation between determinant C and B?
2 times.
2 times determinant.
2 times of determinant of B.
Yeah. Now, if I want in terms of A, I can replace determinant of B with minus determinant of.
Minus 2 times determinant.
So here you see which option matches determinant C.
Fourth option.
That's all.
Ma'am, what was the last
Ma'am,
thing?
y minus 2. Ma'am, y minus 2.
Because determinant of B is minus determinant of A.
Okay.
Because of this. Okay. Got it?
Okay, ma'am. Okay.
So how is it determinant B is minus determinant of A, ma'am?
Because B is obtained by doing row interchanging from A. Row interchanging will change the sign of the determinant.
Okay, okay, okay.
Okay. Okay. So this is some problem which is just understanding what is trace and what is determinant, you know, right? What is mean by trace?
Sum of the diagonal elements.
Sum of all the diagonal
So
elements.
suppose if you have A is, let us say, A, B, C, D. What is trace of A?
A plus B.
What is determinant of A?
AD minus
AD minus BC.
Okay. Now let us consider maybe A, B, C, D is a bad option because
is
Ci
it
is
trace?
given. Let me take A1, A2, A3, A4. Okay. Because here we have C. I don't want to confuse it with this C. So A1, A2, A3, A4. So this is A1 plus A4. This is A1, A4 minus A2, A3. Okay. Now what is A minus Ci?
A1 minus C,
Minus
A2,
A.
A3, and A4 minus C.
Okay. Now what is the determinant of this matrix?
A1 minus C multiplied by A4 minus C minus A2 H2.
Okay, so let's rewrite this. So this gives us C square minus A1 plus A4 times of C and then plus A1, A4 minus A2, A3. Now this part is nothing but trace of A. times C.
Yes,
and
ma'am. Yes, ma'am.
determinant of A. So you see that C square minus trace of A plus determinant of A. This option is correct. This is incorrect. This is also incorrect. This is also incorrect.
Ma'am, trace is, what was trace? Like the diagonal?
Sum of
Sum
diagonals.
of the
Diagonal. Okay.
Also, ma'am, this is a polynomial of C integrated.
Yeah. Clear? Okay. So this
Yes, ma'am.
question, based on the above, can you answer this question? What do you know about a symmetric matrix and the diagonals of a symmetric matrix? Skew symmetric matrix. Sorry, skew symmetric matrix.
Zero.
Diagonals are zero. And suppose let us say that this is alpha, then what do you know about this in
Minus alpha. Minus alpha.
alpha? So in that case, what is your trace and determinant?
Trace 0.
Determinant alpha square.
Alpha square.
All right. So in that case, what is determinant of A minus Ci? C square minus 0 times of C
Plus alpha square.
plus alpha square. So simply C square plus alpha square. That's all is the answer. Is that fine?
Can you explain that determinant of F minus Ci? How will you take A square minus 0C?
How A minus Ci is this?
Okay, and can you explain it?
I just applied this formula which we got it from the previous question.
Okay.
I use this formula here. Okay. So trace is 0, determinant is alpha square. I just applied it in this formula. Clear?
Okay.
Okay. Moving to week 2. Solutions to system of linear equation. If a system of linear equation has a solution, it does not matter it has a unique solution or infinitely many solutions. The system is called consistent, right? Already I told you. So unique or infinitely many, the system is consistent. No solution, the system is inconsistent. First, let us look at the case where we have a homogeneous system. If we have a homogeneous system, Ax is equal to 0, the system is always consistent or inconsistent?
Consistent.
Okay. And what is the what is always there in the solution set?
0 is always a solution.
Yes.
0 vector.
Yeah. So if A is a square matrix and determinant is non-zero, then the system has
Unique
solution.
Unique solution.
Okay. And if the determinant is 0,
Infinite
then
solution. Infinite solution or no solution.
No. Be careful, because we already told the system is always consistent. No solution does not happen for Ax is equal to 0. Okay.
Okay, ma'am. Okay.
So
Yes, ma'am.
only infinitely many solution. Okay.
Okay.
All right. If A is a rectangular matrix, then what happens? If A is an m by n matrix, where m is the number of
Rows.
M
Number of
equations,
number
and
of
n is the number of, right?
variables. Equations.
If m is greater than n, then the maximum value of rank of A is
N.
n.
Not
Value is n, right? So now suppose if we have rank of A equal to n, then in that case the system has
Unique solution.
I did not get this, ma'am.
Unique solution.
Yes, ma'am.
here there is this property for rank of A. Rank of A is less than or equal to minimum of m comma n.
Ma'am,
Okay.
then it should
So
be
now,
n, no?
yes, if m is greater than n, what is the minimum value here?
N.
N.
N, ma'am.
N. That's why rank of A, the maximum value is n. Got it?
Yes, ma'am.
Okay.
Yes, ma'am. Thank
Now,
you,
if
ma'am.
m is greater than n and rank of A is equal to n, then the system has
Unique
solution.
unique solution. And if this rank is strictly less than n, in that case, the
Infinite.
system has
Infinite solution.
Well,
Okay.
can you just tell us a little bit about the rank, because I don't think rank has been discussed in week 1 to 4, right? I mean, I think it is a week.
Rank is there in week 4.
Week
At
4.
the end of at the last lecture, it is rank.
Okay, ma'am. I'll take a look at it. Thank you.
Okay. Okay. If m is less than n, then the system has
Infinitely so many solutions.
infinitely many solutions.
Could you explain this? M is greater than n and m is less than n. Rank is less than n or
Here I
equal
have
to n.
directly given the answer. So this is based on what we call as the rank nullity theorem, which comes much later in the beginning of week 5.
No, when rank is equal to n, then we have all the rows linearly independent actually. In that terms, I am
Yes.
asking actually.
Yes, all the rows are linearly independent. So this means you have the range to be the entire Rn.
Rn.
Yeah. So hence you
Is
have
it
the unique
in quiz
solution.
1 or in quiz 2, ma'am? Because rank is also part of quiz 1, ma'am.
Rank is also
Yes.
part of quiz 1. Yes. Okay.
So,
So,
ma'am,
but, yeah.
the dimension is n. Okay, it covers the whole span the whole space.
Yes.
So how come then unique solution, ma'am? How can we visualize using rank actually?
See, the thing is that here we are using something called rank nullity theorem. So what does, please let's not go into rank nullity theorem here, because that is actually week 5. But here for now, take some examples and see that for m greater than n, rank of a equal to n implies that the system has a unique solution. Because here when rank of a is equal to n, then the nullity has to be 0. If the nullity is 0, this means that the system should have a unique solution.
Then
What is
then we can say that it has n independent equations, not dependent.
See, there can be many way to interpret this, but the basic argument which we usually use is the rank nullity theorem. So here, you what is mean by nullity? Are you familiar with nullity? If you are not familiar with the rank, then nullity is something which I should not use here. That's why I'm not very much comfortable in explaining this part. See, here this part, I recommend all of you remember this. Okay, I'm putting it in red. Remember this part. So maybe I will put important. Remember this. So in week 5 session, let's discuss why this is happening. Okay. For now, for quiz 1, just remember this is what is happening. Okay. Once we are introducing what is rank nullity theorem, at that time we can discuss this. Okay. Fine. Okay. So I don't think I will explain what is Cramer's rule and all. Cramer's rule is,
So
yeah, some
easy.
formula is there. So I will not go into the formula and all. Just
Just give a
can,
glimpses on that.
sorry, what?
Can you just give the glimpses on that?
See, Cramer's rule means basically what? So we are up, as suppose for example we are having a 3 by 3 matrix. So first we will replace the first column with the matrix, the vector b. Similarly, the second row I'll replace it with b and call it ax2, and third I'm replacing with b and calling it ax3. Now for finding solution x1, x2, x3, it is simply using this formula. So here Cramer's rule is applicable only when determinant of A is non-zero for invertible coefficient matrix. Okay. So in that case, this is the formula. Okay. And for inverse, you know that this is the formula where this is the determinant of A. This is the determinant of A. Right. This part is the determinant. So A inverse is 1 by determinant of A into the adjoint of A, so which is the transpose of the cofactor matrix. So here I don't want to spend time in explaining formulas. Formulas you people know. So this is something which I explained earlier. So if you have an invertible coefficient matrix, Ax is equal to B. So what do you have? Ax is equal to B when I multiply A inverse in the front for both. A inverse A is equal to identity. So I have X is equal to A inverse B.
And what is invertible matrix?
Come on, this is not a live session.
Determinant not equal to 0.
The determinant is non-zero. Okay, inverse of a matrix means, so this is a formula for computing the inverse when the determinant is non-zero. Okay, so here determinant is non-zero. Okay, fine. Okay, so the system of linear equation. So if you have this, then write the system into matrix form, and then find the inverse, multiply B with A inverse, then the A inverse B, the elements here are the solutions for x1, x2, xn. Okay, fine. Yes.
Excuse me, ma'am.
Yes.
Just a small advice I'm seeking with respect to the solutions of equation part. Right now, the one approach you told, I understood. In some other sessions, some other approach we learned about the computing the rank and then finding out. So, we in which type of question, which approach to apply? Could you please briefly tell?
For finding rank.
For finding the nature and the number of solutions.
See, that is completely based on what you are used to. So first thing I always recommend is that look at the rank of the matrix, or if it is a square matrix, first look at the determinant. This is the first suggestion I will always give. So first, if it is a square matrix, look at the determinant. Okay, from the determinant itself you will already get some idea. If it is non-zero, I have already given the conditions based on determinant. The other thing is that if you have a rectangular matrix, look at the rank of the matrix. Based on the rank of the matrix, again you have these following observations. Okay, so if to find the rank, again you have to look at the matrix and decide what is the technique you need to do. Whether you can just decide it by looking at the rows or columns, whether they are linearly independent or not, you can do that. Or if you find it very difficult to just find the rank from observation, then you have to go to row echelon form.
Okay.
Okay, fine.
Okay, thank you.
Okay, so now for the system of equation, it is given that the solution is unique. So if the solution is unique, what do you know about the coefficient matrix?
It should be invertible.
Determinant non-zero.
So the determinant is non-zero. What is the determinant of this matrix?
K plus 9.
And
K
this
minus
is 0.
K
So
should
K
be
should
minus
be,
9.
yeah. So this is the answer. That's all. Okay. Fine. Okay. So next we are going to look at what is Gauss elimination method. Okay. What is Gauss elimination method? So when we have a square and invertible matrix, you know, you can find the inverse and find the unique solution. But if we don't have a matrix square which has an invertible coefficient matrix, or if we have just a rectangular matrix where we cannot compute inverse, then in that case we have to rely on Gauss elimination method. Okay. So for Gauss elimination method, first we have to find the row echelon form. So what is meant by row echelon form? We say that a matrix is in row echelon form if the first non-zero element in each row called the leading entry is 1. Right? So for example, let us say you have 1, 0, 1, 0, 1, 2. Is this in row echelon form?
Yes, ma'am.
Yes, ma'am.
Yes. In row echelon form. Okay. Now each leading entry is in a column to the right of the leading entry in the previous row. Now first let us say 1, 0, 1, 0, 0, 1. Now is this in row echelon form?
Yes, ma'am.
Yes, ma'am.
Because we see that the leading entry in any column, okay, is to the right of the leading entry in the previous row. So these are the leading entries. You see that this leading entry is to the right of the leading entry of the previous row, right? So these are in row. These two matrices are in row echelon form. Okay.
Ma'am.
Yes.
Ma'am, I did not understand the second point.
The second part says that, see, what are the leading entries? Leading entry is the first non-zero element. Okay, first non-zero element in each row, that is called your leading entry. Okay, so here this is your non-zero and first non-zero entry. This is your first non-zero entry. This is first non-zero entry, and this is first non-zero entry. So if you take any first non-zero entry, okay, that should be in a column which is to the right of the previous leading entry. So here you see this one is to the right, this one is also to the right. It does not matter whether it is exactly behind it or maybe one step ahead. You just have to see whether it is to the right or not. In that case, we say that the leading entry is to the right of the previous leading entry. Yes, someone has raised your hands. Yes.
Ma'am, so I just have a little question in the first example. So if let's say you switch the rows, then the leading entry in the second row goes to the top, right? And it's not exactly on the right hand side; it becomes the left hand side.
Yes. So
So
second condition fails.
okay, but the job is still done, right? I mean, you still know how many independent
See what?
variables are there.
See, the technique gives us a specific rules, guidelines, but yeah, there are several ways in which you can just, you don't even have to find row echelon form in many scenarios, right? You can straight away do it. So it is our convenience. So for our convenience, they have given some specific guidelines, and these are the guidelines for row echelon form. This is how it is. It should be there. So you can create your own way to find it. But yeah, for row echelon form, this should be there. This
Okay, okay,
condition should be there.
sure, ma'am.
And
Thank you.
here because switching rows are allowed. So I think as the other guy was mentioning, if the row is above, then we can just bring it down.
See, when you are finding rank, when you are using row echelon form for finding rank, what you are saying is fine. But here I am just talking about what are the conditions a matrix should satisfy to be in row echelon form. That is what I am talking right now. Okay. Fine. Rows with all zero elements, if any, are below rows having a non-zero element. Okay. So for example, so suppose you have 1, 2, 0, 1, 0, 0. So all 0 rows should be at the bottom. Okay. So this is the third condition. If all the three conditions are satisfied, then we say it is in row echelon form. Okay. Now what is meant by reduced row echelon form? So for a non-zero row, the leading entry in the row is the only non-zero entry in its column. So for example, take this matrix. Okay. So now this is a leading entry, this is a leading entry. For the first column, in the containing the leading row, leading entry, this is a only leading entry. What about this one?
Mone. Da.
Please mute. Please mute.
Ma'am, that 2 should be removed.
Yeah. So if only the 2 is 0, then only we can say it is in row echelon form. So this is in REF, but not RREF, because here this column is containing a leading entry, but this entry is non-zero. Okay. The leading entry in the row is the only non-zero entry in its column. Okay. So for example, here you see, here this is a leading entry, which is the only non-zero entry.
This is a condition from reduce row echelon form, na?
Sorry, what?
Ma'am, that you say that we have to remove the 2, we have to make a 0, na?
See, only if this 2 is 0, then we call it reduced row echelon form. Otherwise, it is just in row echelon form. Yes.
Okay.
Okay. Fine. So for example, this is in
Ma'am.
reduced row echelon form. Yeah.
In ARREF, if the element in A14, if it was a number, any other non-zero number?
It's not in RREF because the very first condition is violated.
No, not A14, like row 1,
Oh,
fourth
this
element.
one, A14. Yeah. See, if this entry, apart from this, any other non-zero entry, if you have, then that is not RREF. It is just REF.
Okay, but ma'am, I don't know, in some places I've seen only just like in A24, only that place it should be 0.
Yeah, that is REF. That is REF. So for example, this is REF. This is RREF. Reduced row echelon form.
Ma'am, is there any advantage of RREF over REF?
See, RREF, the matrix, if you have the matrix in RREF, computation of the solutions of the system of equation is very straightforward. But if you have an REF, there are a little extra computations. That's all. Okay. And also
Okay,
you
ma'am.
know that a matrix, so suppose let us say RREF of a matrix is not unique, whereas RREF is to some extent is unique. Okay, you cannot have very different RREF forms. Okay.
Ma'am, if RREF, below this 2, if there is a 1, then it's not an RREF, no?
If it is a 1 year, then it is not RREF.
Okay, okay, ma'am. If it's below than this also, in that third, yes, ma'am, here, then
No, not in RREF, because here you have 1.
no, ma'am, in left side.
Here,
Yes, ma'am.
then it is not even RREF, because here you see the pivot elements are to the left, not to the right.
Okay, okay, okay.
Okay, fine. Okay.
So, ma'am, for it to be an RREF, only one should be present.
Yes, yes. In any column, only one should be present. Any column containing leading entry, not all columns. In any column containing leading entry, only one should be present.
Okay.
Like after 0, no?
Yeah, apart from 0. The only non-zero entry is 1. Yeah.
Leading element should be 0.
Leading entry, we never call it 0
Should
as a
be 1,
leading
sorry.
entry.
Should be
Yeah.
1.
Okay. So now we know what is REF and RREF. Now, how are we going to use REF or RREF to find the solution? Let AX equal to B be a system of linear equation where A is in the reduced row echelon form. Note that A is already in the reduced row echelon form. Okay. So consider the case when ith row of A is 0 and BA entry of the matrix B is non-zero. In that case, the system of linear equation has no solution. What does that mean? What does that mean? So suppose let us say A is in the reduced row echelon form. So for something like this, 1 0 0 1 and here 0 0. So you see the third row is 0. Right? Now suppose let us say I have x y here and then I have 1 1 1. So here B3 is non-zero. So if my third row in my RREF is 0 and this B3 is non-zero, then the system has no solution.
No
Right?
solution.
Because what happens? On the LHS you have 0 and RHS is non-zero. So you have no solution. Is that clear? What does this note tell you? Is that clear?
Yes.
Okay.
Yes.
Okay. So now what are the different scenarios?
Ma'am,
A is,
actually, I wanted to ask something.
yes.
In the reduced row echelon form of the matrix, in this example, how is 2 in the row reduced echelon form?
Because this column, no leading entries are there. So this
In
column,
place of 2, any number could have been there. Okay,
yes.
right now?
Yes.
And if last entry wasn't 1, and 2 was another any number was present in the first row last column, then it is also a RREF form.
No, because here you have a leading entry. Any
No,
column
it
containing
wasn't
leading
there.
entry, any column containing leading entry should have only 1 and 0, and exactly 1 1, and the remaining entries are 0.
Okay, but if it wasn't there, the last leading entry wasn't there, then
it can have anything here.
any number, right?
Yeah.
Oh, thank you so much, ma'am.
Yeah.
Somewhere it was mentioned that RREF almost resembles a identity matrix, but that is wrong.
Exactly. No, it's correct. In the case of a square matrix, it is correct.
In this, okay, ma'am. And the REF is almost a upper triangular matrix, right?
Exactly.
Okay.
Ma'am.
Yes.
Ma'am, in this RREF, except of the two in the second.
Sorry, I just want to correctly complete the previous statement which I mentioned. The RREF is equal to identity only if the matrix is invertible. Otherwise, it will not be equal to identity.
Okay, ma'am.
Yeah. The other student, yeah, please continue. Sorry.
Yes, ma'am. Ma'am, in the RREF, where there was the 2 in the second column, if there was a 1 there.
Does not matter. Any alpha, it does not matter. It is still in RREF.
So would the second one be considered as leading entry or no?
Clearly mentioned, this column has no leading entry. The first non-zero entry in any row is called the leading entry. I have boxed the leading entries. This is not a leading entry.
But if there was a 1 there?
That's what I said. Any alpha does not make any difference. You can put any alpha. It's still in RREF.
Okay.
Ma'am, determinant of upper triangular matrix is equal to?
Determinant of?
Upper triangular matrix.
It's the product of diagonal entries.
Thank you, ma'am.
Okay. It feels like I'm
Yes,
going to
student,
write
ma'am.
exam. All are asking questions to me. All right, fine. Okay. So here, unique solutions. What are the scenarios where you will have a unique solution for a non-homogeneous system? Already we have seen the scenarios for a homogeneous system. Now we will look at non-homogeneous system. What are the scenario when we will have a unique solution? Okay. So
me,
here,
ma'am.
yes.
Ma'am, I have posted one doubt in comment box. Can you please answer this?
Sorry, you have doubt where?
Comment box, ma'am.
In the chat window, ma'am.
Oh, just give me a moment. For a m by n matrix, is m is greater than n and rank of A is strictly less than n, then it has infinitely many solutions. This is only for homogeneous system. Yes. This is only for homogeneous system,
Okay, ma'am.
not
Thank
for
you, ma'am.
non-homogeneous system. Okay, for non-homogeneous system,
Excuse
we
me,
are
ma'am.
going to see the, yeah. Yeah.
With respect to that fact, means the flowchart you had given in some red color, that was for only homogeneous. For non-homogeneous, could you please state the equivalent rule? Actually, I got mixed up.
I'm going to tell it now. Okay. We are going to discuss that only here.
Okay.
Okay. For non-homogeneous system, what is going to happen? Okay. So for unique solution, when can we have unique solution? If A is an n by n matrix, A is an n by n matrix, okay, and then you are having determinant of A is non-zero, then you know that you have a unique solution.
This is for
Okay, so this is
non-homogeneous
one
you are telling now, right?
Exactly. Now I'm telling for non-homogeneous. Okay, fine. Now, if A is an m by n matrix with m greater than n and rank of A is equal to n. Okay. Now A is equal to 1, 0, 0, 1. So this is one example I have taken. Okay. So now, for example, here let us state. So what is the size of this particular matrix here?
3 cross 2.
3 by 2.
3 cross 2.
This is a 3 cross. Okay, let me switch the colors. So this is a 3 cross 2 matrix. Okay, so this is a 3 cross 2 matrix. So what is the obvious relation between m and n you see here?
M is greater than.
So m is
And is less
greater
than.
than n. So here m is greater than n. And what is the rank of A here? What is the rank of A?
2.
2.
Rank 2, right? So if rank is 2, then so here rank is 2. Now how many solutions will this system have?
It looks
How
like
many
there's
solutions?
many.
Infinite.
Why?
Infinitely many.
Unique.
Why?
Unique session.
Unique solution.
Unique solution or
It will
no
have
solution.
unique solution. Okay, when m is greater than n and rank of A is equal to n, in this case we have a unique solution. See here we are omitting the no solution case. Whatever we are considering, we are omitting the no solution case. We are assuming that the corresponding, if we have a zero row, we are assuming the corresponding BI is zero. Okay, that assumption is there. Under this assumption, we can say that this has a unique solution. Okay, is that clear?
Ma'am, could you please repeat that one statement regarding the zero row?
Regarding the zero, this one. Okay, so here what I am saying is that, suppose let us say, let us consider two different scenario for the same matrix. So let us take A into xy is equal to, let us say 2 3 and 0, and let us consider another scenario which is something mentioned here. So A into xy is equal to, let us say 1 1 1. Now this solution, this equation has a unique solution where x is equal to 2 and y is equal to 3, and here no solution. Is that clear? Corresponding to the
Ma'am,
0 row, so row 3 is 0 here, row 3 is 0. So B3, only if B3 is 0, I will have a solution. And if B3 is non-zero, I will not have a solution. Is that clear?
I have not understood this.
Yes.
A is M into N.
no.
This part could you please?
Ma'am, actually here X, Y and Z should be also there since the 2, 3 and 0, it is in R3, right? R raised to
You
3.
forgot the basic fundamentals of matrix multiplication, I guess. So if you have a 3 cross 2
Okay,
matrix here, you should have a 2 cross
I'm
1
sorry, ma'am.
matrix, right? Yeah. Okay. So those who did not understand, can you tell which part you did not understand so that I don't spend time in
M
the
is
entire
greater than
M
M
is
is greater.
M is greater than n. Yeah. So
M
here
is the
what?
number of equations, and N is the number of variables.
Yes. Yes.
And rank of A is equal to N, ma'am.
Rank of?
A is equal to N.
Yes. Rank
M
of
is
A
the
is equal
number
to
of
n. Yes.
rows.
Number of
Rows.
rank
N,
of A is column.
n is the number of rows or number of variables, any way you can say.
So
So what's
rank
your
of
question?
any
Columns, I think.
Ma'am, in BIE the third column is 0 in B vector.
Yeah, for this case, here you see that B3 is 0. Here B3 is non-zero.
Ma'am, shouldn't be infinite solutions, ma'am?
See, when we have B3 equal to 0, what happens? Just multiply and see and tell me. Multiply. What will you get? X is equal to 2, Y is equal to 3 is what you are getting, right?
Yes, ma'am.
Okay. Yeah.
And when Z can be anything, ma'am.
There is no Z here. Okay. Someone has
0 is
raised
equal
your
to
hands.
0.
Ask your question.
Ma'am, I just want to
No?
confirm one thing. Hello, am I audible?
Yes, yes.
I just want to confirm one thing. Means we are given a rectangular matrix A with m rows and n columns, and we are observing that m number of rows is greater than the n number of columns. So in that is given. Till now, am I right?
M is the number of, sorry, I did not get what you were saying.
We are given with a rectangular matrix A with m
Yes,
number of rows and n number of columns, and
exactly.
and we are observing that the m number of rows and is greater than n number of columns. Till now, am I right?
Yes, yes.
And in that, given those conditions, if we find rank of A equal to that n columns, then it is unique solution. And given those conditions, if we find that rank of A is less than the n columns, then infinite solution. Is it like that?
Yes. Here infinitely many solution. Here I have not yet come to that part. Hold on. Only when rank of A equal to n, I know that there is a unique solution. Okay. So the next part, hold on, we'll discuss. Okay. Fine. So now when m is greater than n, when rank is equal to n, we know that it has a unique solution. Now, when rank is strictly less than n, what happens? When m is greater than n and rank is strictly less than n, in that case, what can happen?
Infinite solution.
Either it will have an infinite solution. So here,
Or no solution.
see, the no solution case is always there. We are not considering the no solution case. So the other scenario is infinitely many solution. Why is that? So again, it's very obvious, right? So suppose you take, for example, so this is a matrix where rank of A is equal to 1, which is strictly less than 2, right? Now, when you multiply x, y with this, what will you get? X and then 0, 0, right? So there is nothing given for y. So y can take any value.
Ma'am, in this case, B vector, the last two columns are 0, 0.
Yes, it should be 0, 0. Otherwise, it will have no solution.
Okay.
Okay, so here B2, B3 are 0. Otherwise, no solution. Okay, we are omitting the no solution case. Okay. Fine. If A is an m by n less than n. Okay, if A is an m by n matrix, now look at the scenario. We are considering the case when m is less than n. So what happens when m is less than n? When m is less than n,
Infinite solutions.
Infinitely many
Infinite
solutions.
solutions.
again we have only infinite solution. Remember, we are not considering the no solution case. When we are not considering the no solution, we will have infinitely many solutions here. For example, in this case, if I am multiplying with x, y, z, first of all, what is the size of this matrix? 3 cross 2. So you see that m is strictly less than n. Sorry, 2 cross 3.
2 cross
Sorry,
3.
sorry. Yeah, sorry. So this is a 2 cross 3. So m is strictly less than n. So here I also see that what is rank of A? It does not matter what is the rank here. If you just have this condition, automatically you will have only infinitely many solution if you are excluding the no solution case. So here you will have 1, 2, 0, 0, 0, 1. So here if you multiply this, what will you get? X plus 2y,
2y.
and then you will get
Dead.
okay. So let us say this is some b1, b2. Then you see that x plus 2y equal to b1. This has infinitely many solutions.
Excuse me, ma'am, just to confirm one thing, two things.
Yeah.
Like
Tell me.
the above point, A is m cross n and with m greater than n and rank A less than n. Is it no solution or infinite solution? You are explaining something.
Okay, let me maybe summarize everything, whatever we have discussed regarding this, and let me summarize. Okay. So
Yes.
first, let us consider the square matrix case. A is n by n. Okay.
This A is homogeneous or non-homogeneous?
Ax is equal to b non-zero.
Okay.
Okay, because homogeneous case already I have summarized, I guess. So A is n by n, Ax is equal to b non-zero. For this condition, only two things we have to see. So determinant of A, if it is non-zero, okay, if it is, so this is like, let's say this is case 1. So if determinant of A is non-zero, then it has a unique solution.
Excuse me, ma'am.
Yes.
Sorry to interrupt. I just wanted to ask that is the revisions over, or you're just explaining the doubts?
The revision is going on. I'm just summarizing only this part.
Okay.
So the determinant of A, if it is equal to 0. So this means what? Rank of A is strictly less than n. So in this case, two things can happen. So in this case, if B belongs to range of A, or the span of columns of A, then in that case, you will have infinitely many solutions. And if B does not belong to range of A, then you will have no solution. Now,
It means that whether B can be expressed in terms of a column of A or not.
yes, exactly. Whether B can be expressed as a linear combination of the columns of A or not. Okay. Now, suppose we have n.
We can express B in terms of one of the columns, then also we will say that it is infinitely solution.
Exactly.
Okay.
Okay. Now, if m cross n and if you have m is strictly less than n, in this case, so here now we don't have the concept of determinant. Now, the only thing which matters is whether b is there in the range or not. Okay. So, if b belongs to range, then you will have infinitely many solutions.
Many solutions.
And if b does not belong to range, no solution. Your unique solution will not happen in this case. Either no solution or infinitely many solutions. Okay. Now the next scenario is when m is greater than n. When m is greater than n, there are different scenarios. Now, first scenario is rank of A is equal to n. If rank of A is equal to n, then depending on again if B is in range. So the same thing. If B is in range of A, we will have a unique solution. Okay. And if B is not in range of A, no solution. Okay. And if rank of A is strictly less than n, again the same thing only, but here in this case you will have
Infinite.
it will not be unique, it will be infinitely many. So if B is in range, then you will have infinitely many. And here, if B is not in range, no solution. Okay, these are all the possible cases for a non-homogeneous system. All right. Okay.
Okay.
Ma'am, can you
Ma'am, you are
explain
telling
what
that
is
we are
mean by
not considering the no solution case. Why did we neglect the no solution case earlier?
Sorry, what?
Now you are telling that we are not considering the no solution case. Where should we not consider the no solution case?
See, it's not like I'm not considering the no solution case. I'm considering that my B is in the range of A. So in the examples I have specifically considered, I have just considered B is in range of A. That's all. Okay.
Ma'am, can
So
you little
Okay,
bit brief
thank you, ma'am.
about the
So that there is no mistake later. At the earlier part, you were telling at the beginning of the session that was only for homogeneous, right? At the beginning of the session, you were
yes,
summarizing the
yes, homogeneous. That was for homogeneous case.
only homogeneous.
Yes.
Okay, thank you.
Ma'am, what
Ma'am,
is
what
my
should be the rank of the second case in the infinity many solution?
Rank is 2.
Yes.
But here for m less than n, rank does not matter.
ma'am? What do you mean by in range of A? B in range of A? I can't follow.
What does it mean by B in range of A? Range of A is nothing but span of columns of A. Okay. If B is in a range of A means B is a linear combination of columns of A. Got it?
ma'am in form of RREF or REF? Can you say the same thing? The
That's what
range of
I
A.
already. Come on. We are not in the live session. Let's try. We are, see, already it's 10. Let me try to complete this part. This is something crucial in week 2. So let me at least complete what is this. Okay. Fine. So what is dependent and independent variable? We are seeing. Everyone, please be very careful. I am going to talk about what is dependent variable and independent variable. I'm not talking about vectors. I'm talking about variable here. Okay. Please be careful. I'm talking about variables. Okay. Let Ax is equal to B be a system of linear equation where A is in the reduced row echelon form. Assume that for each row of A, the corresponding entry of P is also 0. That is, the system of linear equation has a solution. Okay, I'm assuming that your B belongs to range of A. Here I'm assuming B belongs to range. Okay. Okay. If the ith column has the leading entry of some row, we call xi is dependent variable. And if the ith column does not have the leading entry of any row, then we call xi is an independent variable. So for example, if you take this matrix which we considered earlier, 1 0 or maybe 1 2 0 0 and 0 0 1 0. Okay, so for example, in this matrix, from this matrix, which columns contain the leading entries?
First
1
and
and
3.
3.
1 and 2, C1, C3. So this means you can say that if the ith column has a leading entry, so I can say that x1 and x3 are dependent variables. Okay, and x2 and x4 we call them independent variables. Okay, fine. Is there any relationship between number of dependent variables and rank of a matrix? What is your guess?
Yes.
Yes.
What?
Yes, ma'am.
So what is the relation?
Equal to
The number of independent
total number of variables minus
Number of dependent variable is
is
equal
equal
to
to rank.
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 Remember, we are talking about variables is equal to the rank. Okay. We are talking about variables. Don't confuse it with vectors.
Okay, because in a basis, it's the number of independent vertices, right? That make it a rank.
But number of independent vectors. That is vectors. Don't confuse it with the variables. That's why I'm repeating. It's
Okay.
just variables, not
All right,
vectors.
ma'am.
All right. Okay. Fine. Consider this system. Now, what
Ma'am,
are
just a question on the previous one. Ma'am, dependent variable, that means x2 and x4 are dependent variable here, right? The corresponding x2 and x3, right?
I have clearly mentioned that x2 and x4 are independent variables.
Independent
It does
variable.
not have, yeah.
Okay, okay.
Okay. Fine. Okay. Now for this question, so again it's yeah, very straightforward one. 0 1 0 0 0 0 1 0. So what are the dependent? So this is a leading variable. This is a leading entry. This is a leading entry. So C2, C3 has leading entry. So what are the dependent and independent variables?
C2, C3
x2 and x
X2 and X3 are dependent,
X,
Yeah.
and X1 and
X2
X4 are
and X3
independent.
are dependent. And X1 and X4 are
Independent variable.
independent. Right? All right. Okay, good.
And
So
rank,
how do we?
and rank is dependent, right? So 2.
Yes.
Okay.
Okay. Fine. Okay. Fine. Now you know how in Gauss elimination method we need RREF. How we will be using this RREF to find the solution. So first consider the system of linear equation Ax equal to B. From this form the augmented matrix AB. Augmented matrix means just consider this B along with A. Okay. So here form the augmented matrix. Perform the same elementary row operations on the matrix AB that were used to bring the matrix A into the reduced RREF. So RREF form. So if you want to make A to RREF, whatever the operations you are doing, you have to do it for the B as well. Okay. And then after obtaining the RREF form, okay, this is the resulting matrix, let us say. Now, instead of considering Ax is equal to B, we will be considering Rx is equal to C. And the solution of Rx is equal to C. Computing solution to this is very easy. So, we will compute solutions for this and they are solutions of Ax is equal to B. Okay. So, note that for a consistent system, if the RREF form has no zero row, then the corresponding BI will also have no zero entry. So this is something I mentioned earlier. So if there are independent variables, the solution will have infinitely many solutions, Remember that in this situation. And inconsistent system, if there is a row of the form 0, 0, 0, D, where D is non-zero, then the system has no solution. This is something I mentioned earlier. Remember, if there are independent variables, the solution will have infinitely many solutions. Okay.
Ma'am, can you
Even if one
repeat this
independent variable is
consistent?
there, it will be infinite solution.
Sorry, what?
Even if one independent variable is there where there is no leading one entry, then also it will be infinitely many solution.
Yes, yes. Given this condition. Yeah.
Ma'am, can you
Which
repeat this
actually I can't understand
consistent?
this condition. For consistency, we should have that D equal to 0 or not equal to 0.
For consistency, D is equal to 0. There is no row of this form where this D is non-zero, or equivalently 0 row corresponds to D equal to 0.
Okay, so
Okay.
given that we have a complete 0, if there is at least one independent variable, then infinite solution, otherwise unique solution.
Yes.
Okay.
Just a question here.
Ma'am,
Ma'am,
Yeah.
inconsistent system, I think, ma'am, is the same thing as a B does not belong to range of A.
Yes, yes.
Okay, ma'am.
Okay.
Can you
Madam,
explain the consistent system part again?
Right?
See,
Zero,
the consistent system part, the first condition is just saying that 0 row in RREF form corresponds to D equal to 0. That is the first condition given in consistent system. And then when you have this,
not is
let
equal
me
to 0,
complete.
right?
Please let me complete. So when you already have this condition that corresponding to a 0 row, when D is equal to 0, you have a consistent system. It means you already know that you have a solution. Whether it is unique or infinitely many depends on whether there are independent variables or not. If there are independent variables, then you have infinitely many solutions. Okay, got it now?
The confusion is in the first and the second, both you have mentioned D is not is equal to 0.
So here I have mentioned that, hold on, here I have mentioned that there is a row, and here I have mentioned there is no row
Oh,
of
okay.
this form.
Sorry. Ma'am.
That's why I underlined and circled. Okay.
Ma'am, one more thing. Can you just make one dummy matrix and just show the example for
Okay.
consistent system?
Okay. So for example, take this one. Okay. So here in this case, already the first condition, let us assume. Okay. So let us take a B. So here, this is the B we are having. So this is B1, this is B2. Okay. So this is already satisfying. Here no 0 rows. So no problem for us. We have B1, B2. Now, we have dependent variables. So what are the solutions we will have? So when we write this, it is actually is equal to 1. I don't know. So let us call this some K1, and X4 I call it some K2. So these are any real number. So you have infinitely many solutions. Got it? So the presence of independent variable contributes to infinitely many solutions. Got it?
Yes, ma'am.
Good.
Excuse me, ma'am, for the consistent part, at least one independent variable will contribute to infinite solution. But
Yes.
if there are no independent variables, then what? No solution or unique solution?
Unique solution.
Okay. For the consistent system, I'm asking.
Yes.
Okay. Consistent. Okay. Thank you.
Okay. See, when you don't have any independent variables, then you have full rank. For full rank, we have already seen that you have unique solution, right?
Okay. Yes.
Yeah.
Also, ma'am, in these cases, rank of A is less than number of unknowns. So that also leads to infinite solutions.
Sorry, what?
In this system, means the rank of A is also less than the number of unknowns. So it also leads to infinite solution.
Yes. Okay, so here, can a system Ax equal to B have a unique solution if there are independent variables?
No.
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 Can a system Ax equal to B with no independent variables always have a unique solution?
Yes.
Ma'am, it can have no solution also.
Yes, that is something you need to be careful. So only when you have this condition already given to you, then only you know that you have unique solution. Without this condition, you cannot guarantee that you have a unique solution. Okay, you have to be careful whether this B belongs to the range or not. Okay, this condition is first there and then only we are talking about this. So here the answer is no. Okay, can a system have
Either
a...
unique or it can have infinite, right? In this
Yes,
particular. Okay.
yes. Okay, no, either it can have a unique solution or no solution, not infinite, because you don't have any independent variables, right? So either unique or infinite or no solution, not infinitely many. Okay, because no independent variables, so infinitely many scenario will not happen here. Okay.
Ma'am, can you please show any example of that?
Let's not go to examples. We are running out of time. Let's complete what we have here. So maybe if you want examples, you can ask in the TA session tomorrow. Okay, fine. Suppose A is a 3 by 3 matrix with rank 2 and AX is equal to B is consistent. What can you say about B3?
0.
B3 will be 0.
Yes.
0.
Okay, good. Let's skip this problem. I will tell the TA to try it as a homework, and tomorrow let the TA discuss this problem. Okay, so
Ma'am,
if you have
could you
doubts,
explain?
you can ask the TA. Okay.
Ma'am, could you explain term number 50?
See here, what happens if the rank is 2? You know that last row, that is row 3, is 0. So if row 3 is 0 and the system is consistent, what do you know about B3? B3 should be 0.
0. Infinite
Okay.
solutions in this.
Yes, infinitely many solutions.
And then what about B1 and B2?
What about?
B1 and B2.
B1 and B2 can be anything. Okay. We are only concerned about the entry corresponding to the 0 row. Okay. So yeah, with this we are done. I hope this session was useful. All the best for your exam. Okay. So,
On tomorrow's session, we postpone that. When will be there?
so tomorrow there will be session from 3 to 5 and then you have another session from 8 to 10. So 3 to 5 is a TA session and 10 instructor session. I will schedule it in the calendar. Okay.
Ma'am,
Okay,
ma'am, can you please share this PDF in the calendar?
I will share
please
it
share
as
this
usual
PDF
in the
at the-
drive folder. I will as usual share it in the...
Ma'am, where will we get the drive folder in the portal?
Supplementary.
Ma'am,
Can
thank
someone
you
just share the
for
link
this
in the chat box? Yeah, thank you.